Did you? All right, so what's the role of the program counter?
Make sure we don't get stuck in the recursive loop. Like grading 14 children.
Make sure we don't get stuck in a recursive loop. Where did that come from?
We talked about forking children and getting like stuck recursively.
Well, we definitely talked about forking children.
Yeah.
We definitely talk about.
So you can
track the current count of the functions so you can remember their placements and leave the CPU.
Okay, so the program counter is meant to keep track of which magic trick we last executed on the process, so that we can pick up where we left off next time around.
Hops in and out of the CPU.
Who?
Because it hops in and out of the CPU.
Hops in and out of the CPU. Yep. Which leads us into the other part of the question. Why do we need to keep track of the registers?
To know the current state that each process is in.
And why do we need to know that?
Isn't there a priority for each one?
Okay. Well, why does the process need to know what state it's currently in?
When it comes back to it, it knows where you start back up at.
Okay. Because
or whether or not it needs to run it again. Because it could be.
well, that's true. That probably has nothing to do with the registers specifically, but bottom line is our process data structure needs to keep a whole bunch of crap about a process. The process data structure needs to keep a whole bunch of crap about a process specifically so it can move in and out of the processor, out of the CPU. So it needs to remember where it left off, that's the program counter, and it needs to remember the current state of the CPU, which it keeps track of in terms of the current values of the CPU registers, right? So that's when it packs its bags, then unpacks its bags. Remember that guy? Okay. So it seems like maybe I'm not giving enough quizzes if we're not studying before each class. I need to increase there'll be a higher likelihood of a quiz. Is that it?
You might seem that way, but that's
We're gonna have a quiz every day. Things like that.
Well, if it feels like you have a quiz every day, then why wouldn't you study even for 5 minutes before class, just kind of reviewing what it is we chatted about last class?
We always do that. I come in here and I go, well, what's the quiz going to be on? And everybody goes, I don't know, something about last class.
So the problem is you're surrounded by idiots.
Yes.
The people who come to
Smarter
class.
people around me, and I'm sure I will do better.
You with the upgrade the people around you. Seems like a reasonable plan. All right. So last time we were talking about the process state. That is whether or not it's currently running on the CPU, whether or not it's waiting for some event, typically I/O, whether or not it's in line for the CPU, and that line can take a couple of different forms, as Nick pointed out. We could have some priority, right, within that line. So it's not necessarily first come served, even though that's kind of the human idea of fairness. With a process, we might keep track of the priority of that process, which would not be done in the program counter or the registers, but might be another element that we keep track of in that process data structure, right? Remind me, why are we storing a process in a data structure? What's the purpose of a data structure? Forget about operating systems for a second, just generalistically, computer science specific, I guess. Why do we use data structures? To structure data. Well said. Okay.
To hold information in a way that is most useful for the application of whatever you're doing. So
Okay.
you have different ones, but in general, just to hold information.
So we perceive real life problem solving. We perceive the stuff that's happening around us in terms of the data that belongs to it, the attributes of those things, right? All right, so now why don't we just keep track of all these individual pieces of data kind of just like out on a table or something like that, or just spread all over the computer? Why do we throw it specifically inside of a process data structure?
It's not efficient because you have to search around everything to find what you're looking for.
Okay.
time.
Because humans think about it.
Yeah, okay, so efficiency probably plays in, at least to some extent, but maybe the more human version, the more human answer would be organization, right? We like our stuff to be organized. If we have a drawer where we keep all of our receipts, we put all the receipts in that drawer. Why? Because if we're looking for a receipt, we go and look in the drawer. Except for the one receipt we didn't put in the drawer, right? But in any case, human beings like to be organized, and that's where the advent of object-oriented programming came from, right? So really, would you say a data structure is kind of encapsulated in object-oriented programming? Before that, we just had these grand ideas of data structures, linked lists and sacks and queues, but now we can think of almost anything that we create an object of as a data structure, right? So we're creating a nice little bucket here called the process, and anything we need to associate with that process, we're throwing in that bucket. Program counter, current state of the registers. How do we implement that? Who knows? Maybe it's an array, maybe it's a dictionary, whatever, but somewhere inside of this bucket, we have another little bucket for keeping track of the current state of the registers, right? Maybe we're keeping track of the priority. How important is this particular process? Should it always go to the front of the line? Should it always go to the end of the line? Or would you just treat it as a first come, first serve? Right? What other things might we keep track of a process? Talked about it a little bit last time. If I'm a process and sometimes I'm waiting for the CPU, sometimes I'm running on the CPU, what does it mean for me to be running on the CPU? When it's go time and it's my chance to be on the CPU, I'm like, oh, finally, I've been waiting in line forever. What am I going to do? So I step up to the CPU, and this thing's like a running wood chipper. Just flying. Is it like kind of like the old jump rope thing? Did you ever do that with the double ropes? Double dutch? I used to do the backflips.
Oh, just imagine you do a backflip.
Which performance?
Performance didn't fall out.
Oh, right. Impressive, right? Oh, totally out of context, right? So what does he mean by dexterity and boat performance? Again, euphemisms. Okay, so what was the question? Oh yeah, so we got the running wood chipper. We've stepped up to the CPU. What do we expect to happen? We've decided that the CPU is certainly one of our top resources that we're sharing in our operating system, right? Kind of, we've put memory up there pretty high. Important part of what's going on in our OS. CPU kind of high up there too. Those two guys kind of are, king of the hill. We need kind of both of those to make things cook, right? Okay, so having said that, what's the CPU do? Go ahead.
It just gets in there and says what magic tricks it wants it to perform to complete its task.
Okay, so the CPU does that?
No, the process.
Okay, so the process has to feed it.
Yeah.
Right? So the CPU is like Pac-Man, right? So so on your exam or something like that, you could draw a picture of Pac-Man and then put CPU on it, and that is like part way through the answer, right? So CPUs eat magic tricks. And who has those magic tricks? Who's feeding the CPU? It's the process. And where does the process keep the collection of magic tricks? In the data structure. Okay? And how does he know what the next magic trick he's going to feed the CPU is?
So the processes are stored in data structures and magic tricks.
The process is the data structure.
Okay.
Well, realistically, there would be a data structure that stores processes. That would be the data structure maintained by the process scheduler, which we're going to get ready to talk about. So there's some dude who's in charge of scheduling all the processes, or somewhere he's going to have a data structure for holding all the processes. An individual process is going to have his own magic tricks, the little magic tricks that are associated with the program that process is a representation of which the process is a representation. Dangling preposition of Christian worldview. All right, so God has a sense of humor. All right, so in any case, how do we decide what's the next magic trick we're going to toss at Pac-Man? Toss at the CPU. So the process reaches down into the, how does he know?
The process has to be executed in order, so the process is stored in order needs to be executed and built with magic tricks.
Okay. Really well done at dancing around the answer. We've already answered the question today. I'm the process. I'm reaching down into my bag of magic tricks. Which is the next magic trick I pull out? Which is the next in line?
The one on top?
Think about the quiz we just took, people.
register's not.
The one that notifies the register.
The one that the program counter says we should do?
Oh, sure.
That one? Is that what we all meant to say? So we reach in and program counter says, grab number 8. Here you go. Pac-Man. We throw it at it. Just don't eat me. All right. Man, this level of entertainment is, I'm telling you. All right. And then we increment the program counter to move to the next line. Okay. So that's what the process is doing. Feeding the CPU magic tricks, keeping track of the next magic trick he needs to throw. All right. When he gets onto the CPU, he unpacks those registers onto the CPU. When he's kicked off the CPU, when he's interrupted for whatever reason, when he's interrupted, he's either running back to the ready queue or he's jumping in for an I/O event. Okay, for whatever reason, the CPU manager, all right, the person who's in charge of that CPU walks up to the process, slaps him across the face, says, "You out of here." Okay, for whatever reason, either he's out of time or, look, you're taking up my time and we're not going to wait for you because we're doing I/O or something. Whatever the reason is, that process needs to get off the CPU and he needs to pack his bags. What does that mean? He needs to look at Pac-Man very carefully, copy the current values from the registers, put them into his data structure so he has them for next time, so he can unpack his bags and get out of Dodge. Make sense? Operating system, an incredibly violent place made up of fictional video game characters. Okay. Did you guys see that movie that came out that long ago?
Pixels?
Yeah.
No.
It was actually pretty decent. It really was.
Disgusting reviews on it.
Really?
People were offended. It was.
Oh, my wife and I went and saw it. I thought it was well worth an hour. I mean, you know, this isn't going down in any sort of book for great films. Okay, but well worth an hour and a half. I thought.
Who's starring in it? Was it Adam Sandler?
Yeah, he was in it, but I mean, it was. Maybe that's the problem. You immediately assume it's an Adam Sandler movie. It really wasn't.
Okay.
It wasn't like that.
Wait, did you enjoy it?
Yeah, I thought it was good.
I wanted to see it, but everybody was saying it was awful. But I love Adam Sandler movies.
Oh, but I mean, it didn't feel like an Adam Sandler movie.
Oh, thank you.
Yeah, I mean, he just happened to be an actor in it. So I mean, you know, it had a little bit of slapstick humor, but it wasn't like Happy Gilmore or something like that. You know, it was.
Well, I wish it would be.
Well, you know what I mean.
That's the one good Adam Sandler movie, I think.
One of long as Big Daddy.
Jack and Jill, obviously, next best.
Jack and Jill.
Yeah, Billy Madison also.
You're just like rattling off like Adam Sandler's movie. You know, really, they're all great. I really never thought about it from that perspective. You know, if you just think about Adam Sandler, you just think his whole collection is garbage. But when you go through movie by movie, you realize they're all amazing. What happened?
It's just Happy Gilmore, Billy Madison, and we're all going to laugh at us. That's all you need to know.
Yeah, but it wasn't a typical Adam Sandler movie. I thought it was pretty entertaining. So it's, I mean, obviously kind of a stupid storyline. Aliens invade Earth and decide that,
You know, it used to be, it was a short story at first. It was like a short
Yeah.
movie, and he found the movie, and it was actually a really good movie, and then he made it into a longer movie. I guess it was like a really crappy job or something.
no, I really liked it. A good book if you're into that kind of, vintage. Yeah, Ready Player One. Did you read it?
No, you told.
I've told you about it before. Okay, yeah, I highly recommend it. Highly recommend it. Really good. You've read it.
Yeah,
Yeah. So when you
it's really good. Everybody should read it.
like
It should be a requirement.
minimum of 9 out of 10 stars.
Yeah.
Yeah.
It's really good. I heard it was going to be made into a movie directed by Steven Spielberg.
Yeah.
A few years from now. I've heard he's done with all his current projects.
Sure. Yeah, I think that'll be a really good movie as long as they do it right.
Yeah.
They
They
for instance, Ender's Game was butchered.
Yeah. I mean, they can go in the direction of those really childish movies.
Yeah. I mean, the Ender's Game movie wasn't absolutely horrific, but it didn't match the books.
Yeah.
The books are really good. Okay, so in any case, when we're talking about our processes, we want to think about a post-apocalyptic Pac-Man controlled universe. It's be a reasonable. All right, so we have this thing called the PCB, the process control block. What does this guy keep track of? Process state, program counter, CPU registers, CPU scheduling information, memory management information, accounting information, I/O status information. What would you say PCB is? Based on your understanding from computer science and what we've talked about today, where would you categorize the phrase or the word or the letters next to each other? PCB.
Florida.
Huh?
Florida. Panama City Beach. Spring break. Swing.
Well, it stands for process control block, so we can start with that. What's that the name of?
Oh,
It's the name of the data structure. We got linked lists, we got stacks, now we have the process control block. So this data, this nameless data structure we've been talking about, the process data structure, is called PCB, process control block. Keeps track of process-related crap. All right, so again, same stuff here. What might process state keep track of? Maybe is that one Florida? Is that Florida or Wisconsin or Illinois? Some, you know. Do we have international processes? And does a Canadian process count as international? You need a what?
you need a passport to get
You
there.
need a passport to get there. Well, by passport, I mean, do we need to be encrypted to make? Is this maybe our distributed operating system?
Secure borders.
What do you think we're keeping track of in process state? When you think about, again, our process data structure, the stuff we need to think about, the stuff we need to remember about a process. So if we were to walk up to a PCB, knock on his door, and start asking him questions, he's only going to be able to answer those questions in terms of the things that he's kept track of, right? What's his state? When you were handing, those 5 things, these guys. One of these dudes. Hi, I'm new. Okay, I'm standing in line waiting to meet Pac-Man. Okay, Pac-Man's currently eating the magic tricks I'm throwing at him. I'm waiting for something, just chilling, or I'm done, about to die. That's the process state. So a process needs to know what state he's currently in. Who might ask a process what state he's currently in? Who cares? So if all of us in here, so let's think about this group. Each one of us is a PCB. Okay? And I mean that in the most evil way possible. Okay? Each of us is a PCB. Who might come up to you and ask you what your state is? Who's going to be interested in that information? Register. Probably the scheduler dealy. So register is going to be like, register's like really stupid. Okay, they're not like things that go around and do things. The register just sits there and holds a piece of information, and not even a big piece of information. So the register is like that, you know, the like a little coffee table that you just sit your drink on for a second. When you're done, you pick it up and walk away. It's meaningless in the rest of your life. That's so the CPU is Pac-Man. Registers are nearly useless coffee tables, except when they're useful. Christian worldview. All right, so brought to you by Nabisco. What was I talking about? Oh, PCB. Okay, so you mentioned that it might be the process scheduler. Okay, the dude who's in charge of, you know, wrangling these processes. Like, you go and get in that line. You go and get, you're out of here, that kind of stuff. That person who's in charge of, you know, the line. Okay? So he's going to have to go, and you have all these processes just floating out here. Okay? Programming terms, we're probably going to not just have them floating out there, we're probably going to organize them inside of some other data structures, right? Maybe we have arrays of PCBs, a collection of PCBs. And we need to figure out, so we kind of need to sort them. Like who belongs, like here I have one array, that's the line, that's the ready queue. So, you know, the people who are ready to go onto the CPU, we're gonna take you out of the collection of PCBs and we're gonna throw you into that line. Okay, oh, but wait a minute, you have a higher priority, we're gonna put you at the front of that line. Okay, so the person who's running that, the object, if you will, who's running the process dispatch or the process scheduler, he's going to be very interested in the state of every PCB so that he can do the right thing with them. Okay, what about process number? What's a real life equivalent of a process number? We talked about it in here previously. We called it a PID, process identification, process ID. So we all have social security numbers, right? Unless you're involved in some sort of identity theft, wouldn't every one of us in here have a different social security number? So we have unique social security numbers. Why? What's the purpose of having unique social security numbers? If we want to go the Concordia route, what's the value of having unique FU numbers? Okay. Uniquely identify one student from another student. Uniquely identify one process from another process. Why might that be important? Who's going to be interested in being able to tell one process from another? Scheduler. Same dude. Hey, you, what's your state? What's your ID? You're up. Go meet Pac-Man. Meet your maker, but Pac-Man, I don't think Pac-Man's a creator. Christian worldview. All right. Just layups. What's up? How many times have you thought about Christian worldview so far today? Several times, every time I've said it. Isn't that a Christian worldview? In fact, I keep bringing your attention back to it. All right, so we need to be able to uniquely identify a process. We need to be able to ask a process, what's your current state? We need to know, well, the process needs to know what his program counter is so he knows what to feed Pac-Man next. He needs to keep track of the registers, not for right now necessarily, but for when he leaves the CPU and when he comes back onto the CPU. Okay, memory limits. This has more to do with how the operating system organizes memory. So keeping track of which part of memory do I have access to. Any open files that this process is currently working with. Okay, because files will remain in memory. We'll talk about this when we talk about file systems, but it is very similar to how pointers work. If you have 3 programs that are all looking at the same file, we don't open the file 3 separate times. They all point to the same file because that seems to be more efficient, right? And whoever saves the file last, that's the new version of the file on disk. Okay. So CPU switches from process to process. So all the stuff we've talked about here is our I guess kind of a chart that shows this. All right. So save state, reload state, save state, reload state. What was this called? What's the process of saving your current state? Context switching. Okay, so that's what's happening in here is context switching. Okay, so now we talk about the other player in this, and that's our process scheduler. Okay, so process scheduler is interested in herding processes, herding PCBs. All right, so what's the goal of the process scheduler? Maximize CPU use. Quickly switch processes onto CPU for time sharing. So we want the CPU to be as busy as possible, but we want it to be as busy as possible while being constructive. Go ahead.
Is this a part of the CPU or separate?
Process scheduler is going to be a piece of software. It's part of the operating system. This is the part of the operating system that we've been referencing here that are interested in the PCBs. So all those pieces of information the PCB is keeping track of, many of them are things specifically for the process scheduler. So this is another computer program that's going to maintain several data structures that are going to be various collections of PCBs. Okay, then he's going to have his own logic for how do I fulfill my goals? My goal being I want to maximize the CPU use, but I want the CPU to be used constructively. We can maximize our CPU use by having a machine that's barely doing anything, barely functioning, by just context switching constantly. Okay, our CPU is constantly filling in its registers, exporting its registers over and over and over again, and Pac-Man's starving to death. All right, so
What's context?
context switching is the act of unpacking your bags and then repacking your bags on the CPU. So a process context switches onto the CPU while the previous process context switches off of the CPU. Okay, so a PCB's context is changing, which ultimately for us means his state is changing. I'm no longer running, now I'm either waiting or ready.
Does that mean that Pac-Man is vomiting?
Well, not vomiting. Pac-Man is having his gut copied.
No, he's regurgitating.
Well, that would be vomiting. I think regurgitating and vomiting are synonyms.
Vomiting is like, or vomiting.
Is one controllable, the other one's not
Yeah,
controllable?
regurgitating is like this specific
In
doing it for like.
professional eating, they refer to it as a reversal of fortune.
Wow. Good name.
All right.
So what would be defined as constructive?
Well, constructive would be the CPU actually doing work, spending its time eating magic tricks as opposed to spending its time context switching from one process to another. All right, so ideally we want to have the CPU eating as many. Let's break down how our CPU views time. So we're going to say that the minimal amount of time for the CPU is something called a cycle. Okay, so a cycle is the ABBA. Okay, that's the ABBA. single Pac-Man chomp. Okay, that's a cycle. All right, and we're going to say that so that's the minimal amount of time that a CPU can heat. Everything the CPU does, it does in terms of cycles. Okay, now. The CPU being busy means that a majority of its cycles are spent consuming magic tricks, performing magic tricks, however you want to think about it. Okay, because at some point inside of Pac-Man, inside of our CPU, he has all these little magic tricks programmed as circuitry. So when he eats something, it's not just chewing it and that's it. It has to run it through the right circuit so that the right kind of magic trick occurs. Okay, the right stuff is happening behind the scenes. But for a CPU to be maximized would mean that it's spending most of its cycles actually performing logic, actually eating and performing magic tricks, as opposed to doing other things that aren't moving towards the end of getting problem solved. So now we might say from a process scheduler's perspective, then what we'll do is we'll just throw, we got 5 PCBs. Let's just put the first one on the CPU and just let him run until he's done. We're guaranteed in that situation to have the CPU busy, right? CPU is literally going to work with that PCB until it's done. CPU is busy. But is that considered good? What's one of the goals of the operating system? Well, that's the goal of the process scheduler. One of the goals of the operating system would be for its process scheduler to do its job. But what would be an overarching goal of an operating system that a consumer would expect from it?
To make the system efficient enough to keep the user happy.
Yeah, we want to be happy, which means as we just keep double clicking on crap and having more and more programs open on our computer, we want all those programs to be running in real time at full speed as if everything is happening instantaneously for us, right? So having one PCB run on the CPU till it's done is going to make our other 4 not get any CPU time, which is probably going to tick us off. Okay. User's not happy. Operating system's not doing its job, even though the process scheduler is fulfilling the maximize the CPU role of this. It's not doing that to the best interest of the operating system. Again, we're back to this idea of these thresholds. How do I do my job reasonably well while also maintaining the goals of the OS? that make sense?
With multiple core CPUs that are coming out, can they do multiple PCBs at the same time?
Mm-hmm. More cores, more PCBs. Yep. So, but having said that, the process scheduler's job then gets harder, right? So let's take just segueing off that real quick. Let's take a real life example. So let's say that we have a McDonald's. We'll use McDonald's as our example. So we have one person in the kitchen. Kitchen's understaffed right now. Okay. And, it was a relatively big McDonald's, so it's one of those that has about 8 registers. Okay. It's one of the airport McDonald's. So airport McDonald's, 8 registers, all open, one person in the kitchen. 8 cores. Okay. 8 cores, but the processing can only happen so quickly. So now we're going to keep all those things busy at one time. Well, actually, 8 cores is the wrong example. We have 8 things vying for one resource. And that one resource can only do things so quickly. So even though we have 8 different ways of getting information in, that one resource can't keep up. Okay, so one of the jobs that those individual, I guess the individual registers might have is to feed the kitchen orders in some sort of in-order cadence that it can try to keep up the best it can, right? So maybe you start off by going, okay, order, and just keep going just in a row like that. That's initial human fairness. But now some food orders take less time to cook than other food orders, right? Okay, bag of fries or a cup for soda. Those are almost instantaneous deliveries. Okay? Although you want the fried chicken something or other, that's going to take longer because I hope McDonald's makes those per order. They don't. They just have chicken just sitting there.
No, it's already pre-cooked.
So they crisp fry it. So it's like half fried.
Yeah, it's already cooked, but they freeze dry it.
Oh, I get it. So it's not just ready to. Yeah, I get it. The food is cooked in there, so you don't have to worry about it being underdone. They just need to cook it fast enough to make it so that it doesn't burn and it's not frozen.
Yeah, I think the only thing that's raw are the chicken sandwiches. Those chicken.
Oh, the grilled chicken sandwiches? Are they actually grilled? Or do they just paint the grill marks on it and then deep fry it? Grill marks are barbecue sauce. And we just
Pretty much what happens.
deep fry it. All right. Go ahead.
So, is like the GUI equivalent of the process scheduler the task manager, or is that a step removed from the process scheduler? Or are they not even close?
Is which scheduler?
The process scheduler.
Okay.
Is
Well,
is like the GUI equivalent to that the task manager, or is this only?
Oh, I see. There really isn't a GUI equivalent. The task manager is the user's. It's a similar window. The task manager shows the user the processes that are currently running on the computer. So, but it doesn't. We only have the ability to kill processes, not to say give this guy more priority or stuff like that.
You can say a higher priority for some things.
Yeah, you can do that like in your program.
Okay, so then what you're doing is you're not specifically setting it. You're requesting to the process scheduler that this guy has a higher priority. So it's still, you're not doing it yourself. You can't play a role of process scheduler. Okay, so process scheduler has a couple of queues. It has a job queue. That's all the processes in the system. Okay, so everybody, the whole herd of processes, all the PCBs. Then it has a ready queue, so that's going to be a subset of the job queue. All right, subset of the job queue with only the processes, only the PCBs in there whose state is ready. Okay, now does that mean it duplicates each of these? How can a PCB live in the job queue as well as the ready queue at the same time? This is more of a programming question. If I have a PCB data structure and I add this PCB to our job queue, so an array of jobs, and then I also add him to my ready queue, does that mean that this PCB exists twice? It's a pointer. Yeah, it doesn't exist twice. We've stored the memory address of that PCB in both of those arrays.
So which one's the pointer?
Well, the actual pointer would be the PCB itself. The PCB lives on a memory address, and then these job queues, the job queue, the ready queue, they'll keep track of which memory addresses belong to them. Yeah.
Is the ready queue like what currently has focus on the operating system, and then like the device queue would be like anything that's in the background or something?
Well, the ready queue would be PCBs that are in a state where they're actually ready to get time on the CPU. That's what that guy is. So then we have another set of PCBs that exist but are actually waiting for something else.
Is that like being like suspended or in the background?
Well, not necessarily in the background. I mean, they're waiting on a user to type in a password or something like that. Just because something's in the background doesn't mean it's not also ready. But if it's in the background, chances are that even if it's in the ready queue, it probably has a lower priority. So that's where we start messing around with priority numbers, where if you have an application minimized, you still want it to get CPU time. So if you have Chrome downloading a big file and you've minimized Chrome, you still want that guy to get CPU time, but not at the cost of making one of your other applications slower. We want the operating system to work off this idea that our CPU is sitting idle 95% of the time or more. Therefore, hey, it's going to get enough CPU time to keep that download going, especially since our internet connection is likely substantially slower than our CPU can handle stuff, right? Okay, so our CPU is going to be able to constantly catch back up to where it last left off. So with that in mind, our ready queue is kind of fluid from the perspective of people might be changing their order in line fairly often. PCBs might be changing their order in line fairly often. So device queue, this is going to be all the guys actually waiting for I/O. So device queue is these guys right here. Ready queue is these guys right here. Job queue would be any of these guys. Okay, any PCB that's in existence on the system right now would be in the job queue. They're first added to the job queue when they're new. They're removed from the job queue when they're terminated. All right, makes sense? Our three different queues. All the PCBs, only the ones waiting for the CPU, only the ones that have already been on the CPU that are now waiting for something else. I/O. More than likely I/O. All right, so here, this might be a process representation in Linux using C. So this is C programming. So we have a process ID. This is our unique identifier. We have the state as a long, so state of the process. I wonder why they need to actually store that as a long, since there's only like 4 or 5 or 6 states, depending on how interesting. Time slice, so this is for the scheduler, how much time it's going to get on the CPU. Okay, so this is an unsigned int, probably representing number of cycles, would be my guess. Who this process's parent was, in case it was forked. And then here's the open files. So a structure that keeps track of any of the open files. Whatever. So, but this is a struct representation of a PCB. This is from the C programming language. This predates object-oriented languages. All right. Does that mean that this guy's not a data structure just because it's not represented as an object? Or might the fact that C calls these guys structs indicate that it might be a structure of some type? So the struct keyword was for building our original data structures. What was the difference between structs in a procedural language like C and the evolved struct that is an object in our modern languages like C++ or Java or C Sharp? What differentiates the struct from an object? Every one of you has seen this slide and should have committed it to memory, as you should all the slides I ever put in front of you. Every one of them. It's a slide that talks about the evolution of C, evolution of C++. What's an object? An object is a struct that also includes methods. Okay? So object-oriented languages take all the features of a struct, that is, keeping track of a whole bunch of variable types, a whole bunch of pieces of information, and then adds to it a place to put methods that might operate on those pieces of information. Prior to that, those methods had to live outside of the object because we didn't have an object. So they sat right next to a struct. Okay, so we might think of a struct as a, in somebody's yard, a struct would be a collection of pieces of information. Okay, all sorts of family heirlooms, or let's say we're doing some construction. So a struct would be a bunch of wood, some metal, whatever. And then the functions, the methods, would be a bunch of different secondary machinery that was laying around that we had to take the data to make it work. Okay? As opposed to the object-oriented representation of this, interesting. Object-oriented representation of this, where you would have all that stuff encapsulated inside of a giant tent, and somebody would just yell into the tent and say, all right, I need a 6-inch piece of wood or something like that. We're head bobbing hard here. You see this? This is awesome. Love that. Something like that where all those details are hidden from us because the functions are actually inside.
Is that a one-legged dinosaur?
It totally is.
No, he's got another leg lifted up here. He's ready to pounce. These are 3 toes. Here's the other 3 toes. You see this? This is attack mode or pirouette mode. One of the two.
What do dinosaurs do with operating systems?
It's the Silberschatz Gavin book. They call it That's an interesting question, I suppose.
It would make more sense if it was like Dr. Locklear cosmogony.
Operating systems are old, dinosaurs are old. That's it.
Yep, see, perfect.
Extinct.
All right, so here's some representation of our various cues. Now, when you see these, head, tail, what does this probably indicate to you from a computer science perspective? Not coin flip. Linked lists, probably, right? Why might our job queue and our ready queue and our device queue, why might those guys be implemented as linked lists as opposed to arrays?
Because you can add stuff like this without having to redo the entire thing.
Yeah, because they're going to be constantly changing in size. New processes are being created. New processes are are dying all the time. So things are going to be going in and coming out of the job queue. Same things. Things are going to be leaving the CPU, getting back in line. Things are going to be leaving the CPU, going and entering the device queue, therefore leaving the job queue. So these things are changing size constantly, and that's the benefit of a linked list, right? We can add or remove things trivially at the cost of some performance. But now the reality is performance is less important at this level because we're just keeping track. We're herding all of our stuff. We're not really operating with these structures. We're just moving things out of the front, moving things into the end, that kind of stuff. All right, that kind of makes sense? All right, so for Wednesday, we'll pick up decent chance at another quiz if this one sucked. So we'll might want to review before class, and that's interesting that it keeps bouncing back to the beginning, but whatever. I'll see you on Wednesday.